Hi, everybody. My name is Wyatt Cross. I'm the director of the Montana Water Center. And I want to introduce my co-authors. Whitney Lonsdale is an assistant director of the Water Center. Chuck Dalby, formerly of DNRC, is now with Kintla Enterprises. And Ann Schwen and Sarah Malloy from DNRC. Now, what I want to do today is talk about a project that we've been working on for about a year and a half with the help of many folks across the state about evaluating irrigation efficiency. And what changes in irrigation practice might mean for water supply in Montana. I'm happy to say that our product from this working group is nearly done. It's almost going to print. So we should have hard copies of what I'm going to talk about today, as well as a web product available in the coming month or so. So take a look out for that. Now, this is a topic that's received considerable previous attention in Montana and across the US, and especially the Western US. But there's renewed interest in irrigation efficiency as things like water scarcity, drought, land use change and development, and climate change become all more tangible for us here in the state. This is quite a complex topic and one that I won't be able to cover comprehensively today, but it's critical to point out that irrigation is so important in Montana and so deeply influences and is influenced by our culture, our economy, our policies, and our natural ecosystems. And so each of these realms really needs to be considered to some extent as we navigate this very sort of multifaceted topic. And so what I want to do for the next 15 minutes or so is give you a brief overview of this product with a bit about hydrology and irrigated valleys. I'll talk next about changes in irrigation practice with a bit about the both intended and unintended consequences of these changes. I'll then provide a few examples of how changing irrigation practice can lead to both positive and negative outcomes. And finally, I'll just introduce the concept of adaptation strategies, but because of time constraints, you're gonna have to read the document to hear more about that. So maybe that's a good incentive. Okay, so a bit of background. Irrigated agriculture, of course, has been a huge part of Montana's history and identity since the mid-19th century. Irrigation provides a variety of grasses and crops that contribute to the nearly $4.5 billion agricultural industry in the state. So irrigated agriculture is hugely important. In addition, irrigated agriculture represents the largest consumptive use of water in the state. And this is water that's essentially removed from the system largely through plant transpiration or evaporation. So as a result, how irrigation water is managed plays a massive role in governing water supply and the timing of water availability across big sections of the state. Now, because this is so widespread, irrigated agriculture has also fundamentally transformed the landscape with conveyance infrastructure in irrigated valleys, things like ditches and canals, now finally dissecting river valleys to deliver water efficiently to farms. This is just a zoomed in image of Gallatin Valley near Bozeman, and you can see just how many of these conveyance ditches and canals there are. Now, much of the water that's distributed across the landscape doesn't actually ever make it to a plant, but seeps into groundwater in these alluvial river floodplains. This is an image, a Google Earth image of the northern Bitterroot Valley, showing a variety of wetlands in the northern part that are circled here that have been created by leaky and inefficient irrigation. And these wetlands, of course, now support birds and other wildlife and so on. Okay. There's also been, over time, a large amount of development in these floodplains and new homes and so on. And now it's the case that incidental recharge from irrigation supports an increasing amount of domestic water use as well. In addition, these vast alluvial sponges that are the floodplains slow water down and allow it to slowly leak back to surface waters as something we call return flow, which can actually support a significant portion of stream flow in the late summer, fall, and winter. And of course, these return flows can be absolutely critical for providing, first of all, water to downstream irrigators that have a legal right to this water, as well as native species of concern, such as the one shown here, West Slope cutthroat trout. So this is the system we live in now. It's a brave new sort of irrigated world. Over the past 150 years, we've developed essentially a new hydrology that we're used to and that we've come to depend on. But of course, there are changes taking place. And over the past 50 years or so, there's been a large movement in the Western US and all over the place towards modernization of irrigation infrastructure that enables farmers and ranchers to grow more or different crops while diverting generally less water. These changes in the Western US and Montana have typically been in the form of switching from things like gravity-fed flood irrigation to various types of sprinklers, or the lining of ditches and canals to more efficiently convey water to the farm. Now, Chuck Dalby's talk before mine covered the quantification of these changes, but they have been relatively extensive and they're continuing. So to date, about 20% of flood irrigated land in Montana has been converted to sprinkler irrigation. And although we don't have the numbers, there's been a significant amount of canal lining as well, and some plans to continue that. Together, these changes, these modernizations in irrigation infrastructure are referred to as efforts to increase irrigation efficiency. And when we talk about increasing irrigation efficiency, this is commonly defined as basically increasing the ratio of water consumed by crops to the amount of water diverted from the source. Now, there are obvious reasons for wanting to make these changes, right? And they all make really good sense. Modernization of irrigation infrastructure is reducing the cost and often most importantly, the amount of labor necessary to farm. These projects are increasing the crop production on these farms and can even help reduce nutrient contamination of ground and surface waters, helping to improve water quality. Finally, there have been a number of financial incentive programs at the state and federal level that help farmers basically afford these this modernized infrastructure. But of course, these changes have a massive influence on irrigation water hydrology. And I'm not going to walk through this flow diagram, but it's important to recognize that these changes change the sizes of the arrows in this particular diagram. And one of the most consequential of these changes has to do with the connection between surface water and groundwater. For example, when producers switch from flood to sprinkler irrigation to increase their efficiency, one of the most obvious responses is that less water is applied to the ground, and then therefore less of this water seeps beneath the soil profile. And this means essentially that the quantity of water that each farm has to divert is actually reduced. Now, the same thing happens when canals and ditches are lined. Less of the water seeps into the ground from below the ditch, and therefore less water needs to be diverted for that canal to carry the same amount of water to the farm. Okay, these are increases in irrigation efficiency. It's therefore often assumed, and this is the key assumption in irrigation modernization projects, that these changes reduce loss of water and create water savings that may be applied to other uses. But it's important to question whether these changes actually result in true water conservation from a hydrologic perspective. Does increasing irrigation efficiency really save water? There has been a ton written about this recently, and it's becoming a critical topic in conversations about balancing our water needs with water supply. And in considering whether water is actually saved with irrigation efficiency improvements, we have to ask the question, what was actually happening with this saved water before the changes in infrastructure took place? That is a fundamental question that we need to critically address. Now, in many cases, this extra water was seeping into the vast alluvial floodplains in these river valleys and contributing to stream flow downstream, where it may have been used and reused downstream by irrigators, or perhaps was benefiting fish or other aquatic species. So in this case, water was not really lost in the first place because it was being reused at other locations downstream or at other times of the year. And if we think about when changes in irrigation and conveyance method take place, it may not be saving water, it's simply moving water spatially and temporally within the system. For example, keeping it in the stream at the time of diversion, instead of spreading it out onto the farms and fields and canals and having it return to the surface days, weeks, or months later. And of course, the specific benefits of this or the impacts of these changes on other water users will really depend on when and where water is needed in these other locations across the watershed. Okay, so this really begs the question of what actually constitutes real water savings from a hydrologic and mass balance perspective. So from a conservation of mass standpoint, water is only really saved by reducing the amount of water that's removed from the system, by reducing evaporation in canals and on farms, or reducing plant transpiration from these systems as well. Now, what's interesting is that many of the changes associated with modernization of irrigation may not actually achieve water savings. In fact, a number of studies have shown that conversion from flood to sprinkler irrigation can at times lead to increases in water consumed by crops. How does this happen? Okay, so at the farm scale, this can happen because more uniform and consistent sprinkler irrigation can lead to more robust and dense plant growth. Sprinklers may also allow irrigation on land that was unproductive or previously unproductive under flood irrigation. And if we think about this at a larger spatial scale, at a watershed scale, total water consumption may increase because water left in the stream may be diverted by downstream irrigators who may have been limited by water availability under other flood irrigated scenarios. Okay. Now, there are many examples of this, of how increases in modernization can increase water consumption across the West. One I want to just briefly highlight that's close to home is in the Tongue River Basin on the border of Wyoming and Montana. Here, most of the headwaters of the Tongue are in Wyoming, and the rest of the watershed downstream is in Montana. Now, prior to 2000, most of the conversion from flood to sprinkler irrigation happened upstream in Wyoming. And of course, this was leading to increased crop consumption in Wyoming, additional water consumption, and reduced return flows to the system. This all came to a major head during the drought between 2000 and 2006, when there were extreme water shortages that basically led Montana farmers downstream to file claims against Wyoming, stating that essentially Wyoming's conversion to sprinklers increased water consumption and reduced return flows that were supporting Montana irrigators. In this case, the Supreme Court ruled that the improvements in efficiency in Wyoming were actually permissible under the Yellowstone River Compact. And it's fascinating, it remains the case today that changes in irrigation method on the same acreage does not require state approval, even if those changes might lead to increased consumption. This was something that was identified in our working group as a critical area of policy, but of course still deserves some healthy discussion. Now, in some places, it's the case that the benefits of conversion, and so like diverting less water and leaving more water in the stream at the time of irrigation, the benefits of doing this outweigh the risks or potential impacts of increasing water consumption. This may be especially true in streams or rivers that have sections that are routinely dry in late summer, or where the streams are disconnected from their main stem rivers. And I've got an example here from Gold Creek, a small tributary to the Clark Fork River, west of Butte there. Now, prior to 2007, all of the farms in this relatively small watershed were flood irrigated. And the basic issue was that large diversions for flood irrigation throughout the summer and even into the early fall were leaving the lower portion of Gold Creek completely de-watered in most years, basically severing this connectivity between Gold Creek and the Clark Fork and having an influence on the fishery, the movement and spawning of trout in the ecosystem. In 2007 and 2008, two of the largest ranches at the downstream end here basically, what did they do? They basically changed their irrigation to pipe supplied center pivot sprinkler irrigation. And what this did is it reduced the necessary diversions during the summer and fall and essentially re-watered this lower section of Gold Creek. This reconnected the stream to the Clark Fork and allowed trout to move in and out of Gold Creek to spawn. Now, at the same time, ranches in the middle and upper end of the watershed maintained their flood irrigation, which meant continued contributions of return flows to stream flow lower in the watershed. So here's an example where the particular configuration of flood and sprinkler irrigation, flooding up high, sprinkler down below, actually helped to maintain connectivity at the lower end of the watershed throughout the year. And so I hope it's clear from this example and the example of the Tongue River that the impact of changes in irrigation and conveyance methods on water supply are really site specific. And so each valley or local system will need to understand and assess the potential consequences of changes in irrigation practice locally. And if we think about generalized changes to stream flow hydrographs in response to different types of irrigation, we need to recognize that the shapes of these hydrographs, for example, where they rise, how high they get, where they decline during the year, when things like return flows come back and contribute to stream flow, all of these things will depend on characteristics of that particular watershed or that particular location. And we certainly need much more local data and monitoring to understand these changes. Okay, so I want to just leave you with a few take-home points. The first is that changes to irrigation practice and infrastructure are happening, and they're certainly going to continue in Montana because these changes, the reasons for making these changes are good, and they certainly make sense for folks on the ground. These changes will be very site-specific, and therefore local information about irrigation water budgets are going to go a long way towards understanding hydrologic changes on the ground. And with solid information about hydrologic impacts, watersheds across the state can be empowered to adapt to or actually mitigate changes and try to reduce any unintended consequences where this is possible and where desirable. Now, unfortunately, I won't have time to get into it today, but a large portion of our report is specifically focused on adapting to change and on adaptation strategies, considering the opportunities and constraints of, for example, supporting aquifer recharge while even enhancing crop production. And so we're hoping to have this product printed very soon, and we'll distribute it very widely so you can read all about these adaptation strategies, which are really, really pretty exciting. Now, last but certainly not least, I want to make one last point, and that is that it's important we recognize that there's no one size fits all when it comes to irrigation management. And our intention in this report is not to promote any type of irrigation as a good type or bad type. Our main goal is simply to emphasize that we need to take a very careful and close look at the consequences of any change in irrigation method or practice. And then use the knowledge that we gain from each system to better match available water supply with our varying goals and objectives on the ground. Okay, that's all I had. I'll be happy to take questions, and thanks so much for listening. Take care.